Okay, let's continue with chapter 4. In chapter 4, we focus on advanced encryption standard. And in this chapter, we will start by a simple introduction. Okay, in this introduction, we will review the weaknesses of the data encryption standard, and we will see how we can improve data encryption standard using 3DS. And after that, just a simple mathematical review, and we will go into to see and to investigate the advanced encryption standard, the general structure and the detailed structure, and after that, the different part that we the different blocks of this algorithm, and then we conclude by a summary. So remember that the vulnerability of DOS, mainly brute force attack, it was proved around 1999, and it was one of the most widely used symmetric cipher. But since that time, a big effort has been done in order to replace this algorithm. So one of the approach is to design a completely new algorithm that is resisting to all cryptanalytic and the brute force attack. And this approach produces the new algorithm, which is the advanced encryption standard. And another alternative was to preserve the existing investment in software and equipment, because DAS was already implemented in a lot of devices and services, and to avoid the migration or the modification. So they propose to use multiple encryption with DES. So in this case, what's implemented in software will be the same. The same algorithm is implemented, but they try to increase the key size using what we call triple data encryption standard algorithm. So let's start with the 3DS in order to see how they used DES, and after that we will explain the new approach or the other algorithm, which is advanced encryption standard. So with 3DS, the problem, as you remember, that with the data encryption standard and with the key size of 64-bit, that's then to produce 56 bits, and after that we have different subkeys. Here the 3DDS key is another algorithm where we try to apply the DES algorithm 3 times. So the idea is that we have the plain text. Okay, at the first stage, we apply the encryption algorithm DES with a key K1, which is 64 bits, and then the obtained the text, which is deciphered by this algorithm, will be decrypted by the DES algorithm. But in this case, we will use another key, which is K2. This means that also we are applying a kind of encryption in this case. Okay, and after that, we will apply one more encryption, and we will use K3. So in this case, it's like we apply the algorithm 3 times. Okay, the first one is encryption, the second one is decryption with another key, and the third one is encryption with a third key. It's like we are using 3 keys. Each one is 64-bit, and in this case, it's like we have the DES algorithm with 192 bits. Okay, and this will give a robust algorithm against brute force attack. So at the reception, this is the ciphertext. So here at the ciphertext, we will start by the decryption, and we will use K3 because we have to use the opposite or the reverse steps. So we apply K3 here. So we should decrypt with K3, and after that, we should apply encryption with K2 because we did here decryption. And the third step will be decryption with K1. K1. So here it's K3 is here K1 or K3. Okay. So this is the case when we have three keys. Okay. So we are apply decryption with key 3, then encryption with key 2, and then decryption with key 1. Okay. So if we want to use K1 equal K3, it's possible in this case to use them. So we encrypt with K1, we decrypt with K2, and after that we encrypt with K1. It's like we are using DES algorithm with only 128 bits because each of them is 64 bits. Okay, so this algorithm was used, and maybe in some application now it's still used because in certain application it's with good security. It's according to the application, and that's that approach uh, that maintain the use of DES algorithm in this way. Okay. The other algorithm, which is advanced encryption standard, an advanced encryption standard is a completely new way to encrypt, and it's based on arithmetic operation that we are working in finite field 2 to power 8. You know, in the algebra, this finite field where if you want to define a finite field, we have a set operation, and after that we have that we call the reverse. If we want to have the inverse of any value, so it's typically, for example, like this, b minus 1. Okay, this is the subtraction. If you want to say the division, you don't have division, it's a multiplication with the inverse of b, for example. This is typically something you already investigated in algebra course. We can do addition, subtraction, multiplication, division, and so on, and you have um, the modulo part. In addition to what you know, in the encryption, we have a finite field that is the number, for example, all integer. For example, if we take the set ZP, in this case, it consists of all integers that are from 0 to p minus 1 that are less than p, and p should be prime. And typically in this case, p is a big prime number. And because we are working on this within this finite field, it's like we are working in arithmetic with modulo p. Because in all result, you have the values or the element or the numbers are less than p. This means that if you have any operation in arithmetic way, it should be modulo p because all results are less than p. And typically in encryption, p is a prime number. It's a big prime number. Okay. So here are the main characteristic. Okay, because we work in this case. Okay, and one of the important thing is that if you want to make division means that each number, each non-zero element should have multiplicative inverse. As we said, if you want to divide by b, this means that you are multiplying by the inverse of b. This implies that for each non-zero element, you should have a multiplicative inverse. Okay. It's also important to note that we should have, let's say, a kind of, let's see here, for example, the integer 2 has no multiplicative inverse. So in this case, z to n, we cannot work with this. Okay, so that's why there is some requirement in order to use this finite field for encryption. Okay. So now it's also possible to use a polynomial representation, as you know. And here we want to use the advanced encryption standard within this context. So the idea here is that it's defined by Rijman Demon in Belgium, and we are able to use key lengths for example, 128, 192, or 256 bits. Okay? And typically, if we are using, for example, 256, we talk about AES 256. If you want to use a key length with 128, we are working with AES 128 and so on. In all cases, the block size is 128. Remember that here we are in symmetric encryption and it's a block cipher. Okay, and with the block cipher, we should take a block of bits and process over them. So we do the encryption block by block. Remember that, okay? And it's also iterative. It's not like let's say Fitchel cipher process. It's iterative, and we work on the matrix of 4x4 matrix of bytes. So we have 128 bits, which means that they are 16 bytes, and those 16 bytes are represented as a matrix 4x4. And in this case, this is the block of 128 bits. So the design principle of advanced encryption standard is that we have a good resistance against non-attack, and the speed and code compactness are on many CPU are possible, and the design is not very complex. It's simple design in comparison to the robustness from security point of view. It's robust against attack, so the complexity here is considered as acceptable. It's the design is not complex, it's simple. Okay, so let's see together what's the advanced encryption standard process. So as we said, okay, we have, let's say, something similar, but it's not similar exactly to AES. It's different to the DES. AES is different from the DES. So we have the key generation. Okay, so we have a process to generate the key, and we have different round. Okay, but in this case, we take the 128 bit, which are 16 byte, and they are represented as a 4x4 matrix where each byte is in one element. Okay, so you have 16 bytes, and after that you should apply initial transformation using the key. So here you have a key of m byte. We will see the different possibility, and you will represent them also as a matrix. And after that you have key expansion. This means that you will expand or generate or provide, it's an expansion, different keys or subkeys for the different round that you want to apply. So at each round, you have different transformation. You have 4 transformation. We will see them together. And after that, you obtain the output after round 1 and so on. In round 2, you apply the key 2 and so on. At the end, you will have the ciphertext. Okay. So this is the process of encryption, and here you generate, as we said, different keys for the different round. And typically, if you are using, for example, uh, uh, 10 round, so the key lengths are around 60 byte, which is 128 bits. If you want to use 12 round, this means that you have 192 bits as a key. If you want to use, or typically if you are using a number of round 14, this means that the key size is 256 bits. Okay, so those are typically the value for adaptive encryption, advanced encryption standard. Okay, so those are the parameters. Just I will not let's say repeat them. I will just let you see the expansion key size. This show the different key size that we are using in different round. Okay, because if we have more round, this means that we want to generate more keys for the rounds. Okay, here we have 10 round, so that we have around 176 byte, which is around 44 words. Okay, here we have 12 round, we have 52 words. The number of bytes is 208 bytes, and if we are with the AES 256, in this case the number of round is 14, and the number of words is for the key resulting from the expansion of the key, 60, and the byte are 241. Okay, so this table is very important for you to know the different parameter of the algorithm. Okay, at each case, this could be for AES 128. Those are for AES 192, and those parameters are for AES 256. Okay. So, briefly speaking, we should start by knowing how we can generate the key, because we have the key, okay, and as we said, we have the key expansion, okay, and typically we should start with an initial, a kind of initial state array, and after that we should generate, and this part we call it a key expansion. So if you want to define what's the key expansion, so it's typically the process to generate the different or a series of round keys, because here you generate the keys of the different route, and you are generating them from the original key or from the original encryption key. Okay. And in this case, for each round, you will use one of the expanded key until the final round. Okay. So the expansion, the key expansion should ensure that each round of the advanced encryption standard encryption will use a unique key. Okay, this will increase the complexity and the security of the algorithm. So at each round, the key will be different at each round. Okay, and the expansion process will generate such a unique key. Okay, so if we want to see, this is just the let's say this is the different key I'm talking about, and then here, as I said, this is the key expansion. So we will see that we have the plain text, and this is the plain text. This is the encryption process. This is the decryption process, and here we have the key expansion. Okay, so I will start by explaining the key expansion process in order to see how we generate the different keys for each round. They are different, one from each, they are different, and each one is unique. Okay, and then we will, after describing those key expansion, we will go into the encryption process to see the 4 transformation that we are applied at each round. Okay, which are substitute byte, shift row, mixed column, and add round key. And at the decryption, you will see that here we have the reverse. If we have add key round, it will be add key round. If we have shift row, it will be inverse shift row. If we have substitute byte, it will be inverse substitute byte. So here in this case, we will apply round 1 until round 10, but in a reverse order, okay, in order to decrypt the ciphertext. Okay, so let's start by describing the key expansion process. Okay, so the key expansion process will take the input. Let's say we are talking here in this case using AES 128 bits. Okay, so this means that the key, the original key is 128 bit, which is 16 byte. So the key expansion process in this case will take the input of a 16 byte key and will produce a kind of linear array of 44 words of 176 byte. So in this case, each word is, in this case, 4 bytes. Okay, so this is the illustration. So you will have here from W0 to W 43, which is 44 words. Okay, if each word is a 4 byte, in this case we have 176 byte. Okay. So, and this is, as we said, this is sufficient to provide a forward round key for the initial add key round stage at each of the 10 round of the cipher. So we have here, we have 44 words. So if we take the first four words will provide 16 byte key that will be used at the key round process here with the 16 byte plain text. Okay, and here you can see that here we have 4 words, here 4 words, and so on, and here we have the last 4 words. If we have 44 words, so in this case we have the first add key, and after that we have the 10 round. So this means that we used the 44 words. Okay, so here it's the key for the round 1, key for the, and the last one is the key for the round 10. That's why we have 10 round plus the initial add key round. Okay, now how to generate those words? Okay, the process is like this. The key is copied in the first 4 words of the expanded key. The remainder of the expanded key is filled with the full word at the time. And here, typically, each word WI depend on the intermediately preceding word WI minus 1 and the word first position back. So we will generate each word based on 4 previous one, and then we apply in 3 out of 4 cases a simple XOR. Okay, if you want to see, it will be like this. It will be like this. So the original key, this is the original key. It's divided into an array of 4 byte word. Each word is 32 bits. Okay, here. And then it's split into 4 words. Each contain 4 byte. Okay, and that's why we can see this at this level. So here, okay, we have W0, W1, W2, and W3. And in order to generate W4, W5, W6, W7, we should generate them like this. So W0 is XORed with the result. You apply G over those, and the result will XORed, and you have W4. And after that, you have W5, you have W6, you have W7. So that's the idea here is that you generate each word W based on the previous words. Okay, and this is the G function you apply. So you have here a kind of permutation and a kind of substitution. Okay, so the idea here is that you apply them until having the 44 words. Okay, so the idea here is that using this process, you generate the different keys used for the different round, in addition to the initial add key round. Okay, so this is the way the key is generated. We can go into details and investigating the G function, but at this level, it's not, let's say, we can do it, but it's a kind of, as I say, permutation and substitution, okay? And this will increase the security of the AES algorithm, okay? So this is the idea. The idea is that to summarize is that we have the key expansion algorithm is designed in order to be resistant for any non-cryptanalytic attack. So you have what we call inclusion of a round dependent round constant, eliminate the symmetry between the way in which key are generated in different rounds. That's why you see that at each time here it's generated from the original, and after that you generate them using this process, and G is applied, and so on. Okay, so that's why the knowledge of a part of the cipher key or a round key doesn't enable the calculation of many other key. This is one of the important characteristics. you have an invertible transformation, as you know, and it's possible to apply them on different processor. It's not very complex, supplementation and substitution, and usage of round constant to eliminate symmetry. As we see, we have up to 10, and after that you have the reverse order, and you have the diffusion characteristic, okay, of the cipher, and you have also a kind of confusion. It's not possible to also know if you change any value in the key, it's not possible to detect the relation with the ciphertext. And you have a kind of nonlinearity that's coming from substitution. And you have also a simplicity in the decryption, as you say. What we still need just to go into detail and to CG, but the process is very clear. Okay. If we want now to go to the detailed structure of the advanced encryption standard. So after defining and having the different words that are the key, let's see what are the different steps that we apply to achieve the encryption. So here, the main steps are to substitute byte, to make shift row, then to make mixed column, and then to add round key. You can start also by add round key at the first. This is the initial. This is the initial add round key here. This is the initial one. Okay. Let's remove this. This is the initial add round key. Okay. So if you want to make the add round key, okay. So in this case, we should make an addition, a simple XOR. Okay, the cipher begin and end with add round key. What's an add round key? It can view the cipher as an alternation operation in the XOR. So you XOR the block, okay, and then it's a kind of XOR operation between the plain text and the key. Okay, and as you know, its state is reversible. Okay, so after doing the add round key, let's see together what's the shift row. This is the add encryption, IES encryption. This is the substitution. Then you have the shift row. Then you have the mixed column, and after that you have the add round key. So let's start with the substitute byte. So we are already aware about what's substitution. So in this case, we have a well-defined substitution matrix, and you try to use this matrix in order to continue the substitution. So that's why, because you are waiting on 4x4, okay, so here each byte of state is replaced by a byte indexed by a row left 4 bits and a colon 4 bits. So that's why here, in order to define, okay, because here you have the left 4 bit and the colon, you have the right bit. So you define here, and after that you have X and Y, and this is the value that's substituted. So this is S box, okay, and we can continue like this in order to receive what's the new value. Okay, so this is S prime 1 1 and so on. So it's a classical substitution, but we are doing the substitution at byte level. Okay, so the substitution here is done at byte level. Okay, this is an example of SBox. Okay, this is an example of SBox, and if we specify, for example, the position 0111, it will be here, for example, and let's say 1111, it will be F. So the result will be like this. It will be T2. Okay, and so this is the inverse SBox, because if we are doing at the encryption, if we are using this SBox at the encryption, so we will use the inverse SBox at the decryption. So the SBox is designed to be resistant to non-cryptanalytic, okay, cryptanalytic attack, in order to avoid any relation between the the input and the output of the Xbox, and they developed this design in order to have low correlation between the input and output bits. Okay, and the property that the output is not a linear mathematical function to the input, and in this case we can avoid different attacks, including a linear attack. Okay. The second step is what we call shift row. Okay, here in this case, after having the first step of substitution, we obtain the block of 128 bits, which is represented on 4 by 4 matrix. Okay, here, and in this case, the circular shift is done as follows. So the first row will be unchanged, so you will not change the first row. The second row, you will move 1 byte circular shift to the left. So here it was S10, S11, so S11 will be here, S12 will be here, S13 will be here, and S10 will come here. So that's one byte circular shift to left. And the third row here, we will have 2 byte circular shift left. This means that S22 will be here, S23 will be here, S20 will be here, and S21 will be here. And for the fourth row, we have 3 byte circular shift to left, and in this case, S33 will be here, S30 will be here, S31 will be here, and S32 will be here. And we obtain the shift row. So this is the output of the shift row process. Okay, and we decrypt using the inverse shift. Here it was the shift to left, so we will apply the same order but to right. Okay, and here it's also an important point, because here you apply a kind of a shift, and this shift is applied column by column, as you can see, row by row. Okay, it's possible also to use other state, but here we apply them row by row. This means that we mix them. Okay, and here the main idea is that we will not keep the same column. The transformation here ensures that the 4 bytes of one column are spread out of 4 different columns. That's what's happened. If I have S0, S10, S20, S30, here we have S00, we have here S10, we have here S20, and we have here S30. This means that the byte of the same column are, after transformation, are spread out to the 4 different columns. Okay, and the last transformation is the mix column. Okay? This is also one of the important. Step in the AES encryption algorithm, because it will also increase the diffusion between the cipher, the plain text, and the cipher text. And here we make a kind of, let's say, mix in order to make the attack very difficult. Okay, it's not possible to deduce any information about the about the plain text if you have the ciphertext. So the idea here, because we are working in Galois field 2 to power 8 using the advanced encryption standard algorithm, this means that we are using this polynomial, which is x to power 8 plus x4 plus x3 plus s to power 8 plus x to power 4 plus x to power 3 plus x plus 1. And this is a polynomial Galois field. So the inverse will be done like this. Okay, so The state is represented, as we said, by 4x4 matrix, okay, here. And each column will contain 4 bytes, okay. Each column will contain 4 bytes. And each column is transformed into a new column using a mathematical operation. Okay, so in this case, here you have this column. Okay, if you multiply the column with a row here, okay, so you will obtain new values here. So this is a transformation using this calculation. Okay, so this is typically the way how to proceed. And this mathematical operation will combine the value of the byte that are in the column. So this mixing operation, as we said before, makes the cipher resistance to different attack. It's not possible to have a linear relation between the ciphertext here and the plain text here. Okay, so this is typically what we call a mixing column, mixed column operation. Okay. So the coefficients of the matrix based on linear code, which is the maximal distance between the code word, ensure that a good mixing among the byte of each column. So the mixing column transformation combined with the shift row transformation ensures that after a few rounds, all output bit depend on all on input bit, but we cannot find any clear relation between them. Okay. So let's continue. Let's continue. By the add key round, we already explained this one as initial. So here, the idea here is that you add this one with each word. You have here 16 bits, 16 bytes, sorry. And you have here 4 words. Each word is 4 bytes. They are also 16 bytes, and you add them. So it's a kind of XOR, okay, and you obtain the ciphertext after, or the output after doing the add round. Okay. At the decryption, it's just you are using the inverse of key in the inverse, which is the reverse of key. Okay. So you are using the key in a reverse order. Okay. If you are using the XOR with the add key round, at the first it will be W0 W3, it will be used at the end in the decryption. The last one used in the encryption was W40 until W43. So they will be used as the first add key round during the decryption. Okay. So, and this is typically the substitute byte information. We already presented this, and this here the add key round. Okay, this is an illustration. So, and the importance of that key round is that it's simple because it's just a kind of XOR, okay? And this operation is viewed as column-wise operation between the 4 bytes of the state column and the 1 word of the round key, and it's a byte level operation. It's like this, okay? So here we can see an example. We can see an example here. If you want to see this example, here, okay, I want just to okay. So here I want to let you know the different keyword here. Here you have W0. This is an example where we generate the different word W0, W1, W2. And after that, we see how we obtain W4 from W0. Okay. Z1 is produced here, okay, based on the different operation that we apply. So here we can see the G function, okay, the different block of the auxiliary function, G function, and so on. So that's how we can obtain the different key word. Typically, W0 and W3 are given from the original key. Okay. And here is an example of AES, how we can have the plain text. This is the plain text. Okay. And here is the key round that we obtain, this one, the first one here. Okay. So, and typically we make the add key round and we obtain, this is the first round, the second round, and so on. And here we obtain at each step, this is the substitution, and this is the shift row, and after the mixed column, and after the key round, and so on. This is the first round, this is the output of the first round, and so on. And we can continue. Okay. This is the key that we are using at each sorry, this is the key that we are using at each. This is what we have at the start of each round. Okay, and this is the this is the round key. This is the round key, and this is the output that we have after each round. Okay, we start by the round key, and after that we continue. Okay. If you want to see the avalanche effect, if you remember that we want to see the difference between the plain text and the ciphertext in order to evaluate the diffusion. So here we have two plain text. The only difference is with one bit. Here we have 0000001, and here we have all R0. Okay, so there is only one bit difference. And we can see that at the first round, at key round, we have only one bit different. And after the first round, we have 20 bit difference. Two round, we have 58. If we continue until round 10, so we have around 58-bit difference. It's not so far from the half, which is 64. So at certain time we have 64. Okay, but we continue up to round 10 because we want to have the algorithm be a resistance against all different type of attacks. So, okay, because we want to use a key size 128 bits, and the avalanche effect here, the change in the plain text of 68 is close. It's not so far. It's close to 64 to be the half. It's approximately to be the half. Okay. And if you want to see here the change in the key, this means that if you want to change regarding the key, you are using the key. So here you have, this is the plain text. You are using the same plain text, but for the first one you are using a key, and for the second one you are using another key with only one bit difference. And here you can see that you when using the first round you have only one bit difference, and you have 22, and after 10 rounds you have around 53 bit difference between the two ciphertexts, which provide also a good, it's not so far from 64, but it's good, typically considered as good diffusion, confusion here, because any modification in one bit in the key will generate approximately half for modification of the number of bits in the ciphertext. Okay. So here we will see the inverse. So as we said, the AES decryption cipher is not identical at the encryption. So we have, let's say, two separate chains need to bring the decryption instruction in line with the encryption instruction. So you consider the first two stage of the decryption round need to be interchanged, and the second two stage of the decryption round need to be interchanged. So that's why when you see here, okay, the relation between encryption and decryption, okay, and I can clarify this. So here you have substitute byte, shift row, and add key round. Okay, here you have add key round, And after that, you will have, this is the inverse, this is the substitute, this is the add key round, and this is the inverse of mixed column. So they are at this level, and you will continue like this. And here, this is the inverse shift row, this is the inverse substitute byte, and this is the inverse process of add key round. So that's why you will use them at this level. So this is the decryption process. Okay, that's why we say that in this case, in advanced encryption standard, decryption is not really identical like encryption. Okay. And we have interchanging between inverse shift row and inverse substitute byte. Okay, we already said them. And we have also interchanging the add key round and the inverse mixed column. I already presented them. And you can see that here we will apply those at this level. Okay, and we will continue here, here, in order to use them in a right way. Okay. And after presenting advanced encryption standard, it's well used now. It's used in a lot of application, and it's can be implemented in an efficient way in 8-bit processor. The operation are not very complicated, okay, and it work now. It's applied in a lot of application, okay. And it also can be implemented in 32-bit processor, in 64-bit processor, and the time is the time of encryption and decryption is not a big time. Okay. So, and for the security, now AES with 260-bit key size is considered as a robust algorithm. It's used in a lot of applications, and it's not possible, let's say, to attack it because you need a lot of time to do it. So it's considered as a secure algorithm. Okay. If we want to summarize, now we started by 3DS and we see how we applied DES. And then we presented the AES structure, the key expansion, how it is done, and then the different transformation and the implementation. Okay, so now we presented the most important block cipher algorithm. We started by the classical one, the conventional one, and then we go to the modern cipher, was DS, 3DS, and now AES, which is widely used. Okay, and you know now the difference between AES and DES, and why with AES we have more security, is more, let's say, robust against attack. Okay, and especially we can see the different transformation function. Okay, here I would like to ask you to try to apply this this example, try to apply this exercise. So you have the plain text. You should represent this plain text as the 4x4 matrix, okay? And you should also apply this key. It's really a simple key. Huh? I give you a simple key. Okay, at least start by doing the W0 to W3 and use them in order to make the different initial add key round and then the value of substitute byte, shift row, and mixed column. It's very important for you to check this. So I will provide you also with the answer of this, but you should try to apply it. Okay. So this will end this chapter, and I hope that in the next chapter we will start with asymmetric encryption. Okay. Okay, thank you. If you have any question, you can ask, please. Okay.